Hi everyone, I hope you're ready for an exciting journey into the world of satellite development. My name is Tom, and today I'm thrilled to share with you how you as a developer can dive into the fascinating realm of satellites without even leaving your home. We often believe that gaining experience in satellite development requires being in a specific environment or having specialized opportunities. It's like the old catch-22 situation. You need experience to get a job, but you can't get a job without experience. But here's the exciting part. Just as aspiring game developers create their own small games to gain experience, we can do the same by playing with satellites. Today I'll provide you with an overview of how you can learn more about satellites, experiment with actual projects, and broaden your horizons within this captivating field. In my day job, I lead a research and development team at Morgancoat. However, my passion for technology extends far beyond the 9-to-5 grind. During my free time, I love immersing myself in diverse technological pursuits, ranging from electronics to satellites and amateur radio. I've actively participated in software development for satellite tracking, telemetry reception, and even data transmission via satellites to other enthusiasts. Today, I'm thrilled to be able to share my experiences with you. My own interest started in 2015 when myself and friends decided we wanted to launch a high altitude balloon. Now if you aren't familiar with it, it's basically a weather balloon. We built various payloads that we hooked onto a balloon along with parachute that will float to about 30 kilometers high. Around about that height it bursts, and then we go track the payloads coming down. The requirements for these payloads are very similar to satellites in space. In fact, some of the launches I've been involved with have been used to test out satellite prototypes. It's cheaper than launching a rocket, and only to discover that it doesn't work properly. Once we received the payload on our first successful flight, this was the imagery that we captured. This specific image is what got me hooked onto satellites. This has evolved into getting my amateur radio license and learning more about satellites. It has involved in quite a bit more than what I initially planned. As you can tell, my neighbors love me with all my dishes and rotating antennas. But why should we be interested in satellite development right now? Well, the answer lies in the ever-growing significance of this field, from providing essential communication services to enabling weather monitoring and contributing to scientific research. Satellites play a pivotal role in our modern lives. Companies like SpaceX have also brought down the cost considerably, allowing smaller companies to be able to launch their own satellites. It's very possible that one of your future job opportunities can come from a company involving with launching their own satellites, or at the very least running tech on satellites. Throughout this presentation, I'll introduce you to exciting projects I've been involved with and share the basics of getting started. I'll also discuss some of the many topics in space development to empower you on your satellite development quest. Let's start our exploration into satellite development by delving into how satellite orbits work. Satellite orbits are the very carefully calculated paths that satellites follow around celestial bodies like the Earth. Understanding satellite orbits is key to comprehending how satellites operate and fulfill their specific missions. There are various types of satellite orbits, but today we're going to be focused on two commonly encountered ones: geostationary orbit and low Earth orbit. First, we have the geostationary orbit. Picture a satellite hovering over a fixed spot on the Earth's surface, seemingly suspended in the sky. Satellites in geostationary orbit are positioned high above the equator at an altitude of approximately 35,000 kilometers. These satellites match the Earth's rotation speed, enabling them to remain stationary relative to a particular location on the ground. The stability has advantages for applications like communication and broadcasting services, where consistent coverage over a specific area is essential. For instance, geostationary satellites are responsible for delivering satellite television signals to our homes. Satellites used by DSTV are essentially geostationary satellites. Secondly, we've got low Earth orbit satellites. Unlike geostationary satellites, satellites in LEO are positioned much closer to the Earth's surface, typically a few hundred kilometers above. Instead of being fixed in one spot, these satellites continuously orbit the Earth at high speeds. They complete an orbit in about 90 minutes, swiftly circling our planet and due to the proximity to Earth, LEO satellites offer advantages such as lower latency for communication and more detailed observations for Earth monitoring and imaging missions. Notable examples of LEO satellites include those involved in Earth observation, weather monitoring, and even some internet connectivity products like Starlink. It's worth noting that there are additional orbit types, including medium Earth orbit and highly elliptical orbit, each with their own specific characteristics and applications. Each orbit type is carefully chosen based on the specific mission requirements, such as coverage area, communication latency, or scientific observations. Satellite orbits are precisely calculated using scientific principles and mathematical models. Factors such as a satellite's altitude, speed, and the gravitational pull of the celestial body it orbits determines its orbit path. These calculations consider complex dynamics, ensuring the satellite's stability and functionality throughout its operational lifespan. As we deepen our understanding of satellite orbits, we gain insight into how satellites can fulfill various tasks and meet the diverse needs of modern society. It's a captivating field that blends science, engineering, and innovation to push the boundaries of what's possible in space exploration and communication. Space development is truly one of those industries with lots of different things happening, meaning that there's some kind of development interest for everyone. Some of our basic categories we can look at is ground control software. This typically includes satellite tracking, mission planning and scheduling, analysis of satellite data, and also control communications to and from the satellite. But this can expand to various other parts such as processing of signal, telemetry processing, and other specialized functions depending very much on the purpose of the satellite. We can also chat about the onboard software. This is the software that is running on the satellite itself. This includes the basic functionality of an operating system with various subsections such as power management, data handling, communication protocols, and fault tolerance. And then we also have payload software. So apart from the common software running on various satellites, each satellite has a unique purpose or mission, and the different operations or experiments require software for control and monitoring. But regardless of which area you want to play with, we need to start with the basics of satellite tracking. Satellite tracking involves monitoring the movement and position of satellites as they orbit the Earth. It's a crucial aspect of satellite operations because we need to essentially know where the satellite is at all times. We can't communicate with a satellite if we don't know where it is. So let's jump into our first project where we try to track a satellite. As an example, we will create a very simple application to calculate where a satellite is at any given time and, more importantly, where it is in relation to our ground station. To calculate this, we need the information on the orbit of the satellite. This is conveniently provided in a format which we call the two-line element. This is essentially two lines of data that describes the orbit of the satellite. Combining this with the GPS coordinates of our ground station using great Python library, we can calculate where the satellite is at any specific time and when it will be in view of our ground station. These TLE files, or two-line element, are created and maintained by various space agencies around the world, and also by the actual satellite owners. The creation of these parameters can turn into almost a complete presentation of its own. But the basics that you need to know is that the initial TLE is calculated from the rocket launch parameters, and then it is continuously updated by plotting the received signal over time using specialized software. We don't actually need to go into too much detail on that, just know that the TLE file or data gives us the parameters needed to figure out where the satellite is. So where do we get our TLE data? Well, we get it from a website called the SatNox database. This is a database of almost all the satellites launched with their current status, transmitter info and history. This is part of the SatNox project, which will always also play an important role in our ground station, but I'm going to chat a bit more about that later. As a quick example, let's create a basic Python test application that we can use to track a satellite. We are going to look at a satellite that was recently launched called the Geoscan Edelweiss satellite. It was launched as a technology demonstrator, but with interesting payloads to promote education around satellites. One of the features is a camera taking beautiful pictures of the Earth and then transmitting them to ground stations across the world. For our example, we will be using the Skyfield Python library. It does all the hard maths for us in calculating where our satellite is. Our inputs for this is our TLE data, our current location as the observer or ground station, and then based on the date and time we can calculate where the satellite is. For our example, we'll be using the Skyfield Python library. It does all the hard math for us in calculating where our satellite is. The inputs for our code is the TLE data, our current location as the observer, in other words where exactly we are located, and then based on the date and time we can calculate where the satellite currently is. So running this code, we can see that our satellite is currently at azimuth and elevation in relation to our ground station. But what exactly does this mean? Well, if you were to point an antenna to the satellite, the elevation would be the angle from the horizon to the satellite. Azimuth tells you which direction to the horizon you need to point it. 0 degrees and 360 degrees is at north, moving in a clockwise direction. Any elevation less than 0 degrees means that it's not in our view. The satellite, based on the current time, was at minus 31 degree elevation, which means it was below my view. It will only be in my view from 0 or higher. Knowing this, let's update the code to calculate the next couple of passes, meaning when will the satellite elevation be above 0 degrees. If we run our simple example, then we can see that the satellite will pass over my house multiple times on the 20th of May. Keep in mind that the point of max elevation does not necessarily mean at 90 degrees. This will be different depending on its orbit. But for that pass, that is the highest elevation it will have. I've added a polar graph to visually show what I mean. This is obviously a very simple example, but it's the basics of a satellite tracking application. This can now be expanded with a nice graphical user interface where you can select different satellites, or you can even plot the satellite movements. This is a very fun project which will help you understand how satellites travel and how to track them at any point. You will notice that satellites in lower Earth orbit that are closer to Earth will only be visible for a few minutes, and the further away the satellite is, the longer it will be in our view. Geosynchronous satellites will always be in view. This explains why your DSTV dish does not need to be rotated continuously to point to a satellite. So now we know where the satellite is, and we want to try and get some information from it. Depending on the functionality of the satellite, it can transmit anything from a Morse code beacon to telemetry, information, pictures and more. The simplest hardware requirements to receive a signal from a satellite is to have a radio device hooked up to a computer and an antenna for that specific frequencies. For the radio side, we are using a simple software-defined radio dongle. This is a small USB dongle that looks like a memory stick, but it also has a connector on it for attaching an antenna. For the most part, you have the option of two different antennas. Either a directional antenna, which requires it to be pointed to where our satellite is, or an omnidirectional antenna which does not get pointed but can receive signals from all sides. The difference between the two is that the omnidirectional antenna needs a much stronger signal, where the directional antenna can be pointed to a lower power transmission. Both of these antennas can be made easily at home with bits and bobs from a hardware store. For example, this directional antenna was made with an old tape measure. You can also use various lengths of copper, aluminium to make your antenna. The dimensions of the antenna depend a lot on which frequencies the satellite you want to receive from. There are various online calculators available that will give you the dimensions on how you need to assemble your antenna. For information on the frequencies the satellite transmits on, I refer you back again to the SatNox database where we got our tracking information from, as it will also show which transmitters are active on the satellite including their frequency. This is pretty much the simplest setup you can put together to get started. But while this sounds simple, you can have great results. For example, I've used a similar setup to chat with an astronaut while he was on the International Space Station, while the space station was crossing over my home. And yes, from our point of view, the space station travels and can be tracked in pretty much the same manner as satellites, because it's essentially also a satellite, just much bigger. From a software point of view, we need software that will show the received signal from our satellite. Depending on the software-defined radio you have, there are lots of options. But two of the popular ones is SDR Console and SDR++. SDR Console is a Windows-only version where SDR++ can be run on different platforms. Both of them, however, cover the majority of different SDR dongles currently available. If you have the knowledge, then developing your own SDR software can be done. But for more simpler projects, you can look at demodulating and decoding the received signals. Demodulating the signals means taking the received radio signal and converting it into binary representation. This is usually done by piping the audio received from the signal on your SDR into a separate application that performs digital signal processing. If that sounds too complicated, then you can start even simpler by using software to demodulate the signal into its binary data, and then you develop an application to decode the binary data. What the binary data presents usually depends a lot on what kind of information the satellite is transmitting. Here's an example of receiving a satellite live that's busy passing over my house. This was a video I recorded a while back, so the dates are not recent. But essentially the satellite was called the FalconSat, and you'll notice that as the satellite, as I'm receiving the data, the other software is busy demodulating and decoding the data. This specific satellite is almost like an old school BBS, where you can upload messages on the bulletin board and also download messages again. So you could essentially leave a message on there for somebody else that's on the other side of the world. It's just a fun example of one of the things you can do with these kinds of satellites. Many satellite operators, especially the ones using the amateur radio bands, will release a document with the specification of the transmitted data. Based on your skill level and interest to go down the rabbit hole, you now have a few projects you can do to learn about how satellites transmit, how to receive them, and how to decode them. With this specific setup, you can also participate in satellite telemetry hunting. This is essentially when a new satellite gets launched, enthusiasts around the world who can try to see who can receive the initial signals first, and they also continuously track the signals. It's a lot of fun. Another fun project to do is to learn more to automate the various bits of what we've discussed. This is where I get to chat a bit more about the SatNox project. The SatNox project essentially is a Raspberry Pi based project which you can put together to automatically track satellites, but also receive and record their transmitted signals. This is great for satellites that only pass your home late at night or at any time that you aren't there to receive the signals. The SatNox project allows you to network your ground station and gives you the ability to help others receive satellite data from satellites passing over your home, or for you to get data from satellites on the other side of the world. From an equipment required perspective, all you need to do is to add a Raspberry Pi to the SDR dongle and your antenna. The web interface will allow you to specify various satellites and schedule your ground station to listen for them at the right times. This setup works great for omnidirectional antenna, as you don't need to point it anywhere. But if you want to go to the full Monty, then how about building an antenna rotator that can be controlled by the Raspberry Pi? Once it is all set up, then it will follow the satellite path automatically to make sure that it gets all the signals. The SatNox project shares different designs where you can 3D print most of the rotator. It also has various 3D printable designs for different antennas. I've built a basic antenna rotator using an old heavy-duty camera pan tilt device. The project consisted of a motor driver with an Arduino. The Arduino is connected to a PC or a Raspberry Pi and receives the azimuth and elevation values from the calculations, and then it moves the motors to the right spot. It's a fairly simple setup, but once it's calibrated, you have another powerful tool in your satellite hunting arsenal. Everything I've mentioned up to now allows you to track satellites and receive telemetry. But what if you're interested in software development on the satellite itself? While the cost of satellites and launching them have gone down considerably in the last few years, it's still quite expensive if you only want to learn. But if you think about it, a satellite is basically just a small computer with sensors and a small transmitter. The only real difference is that the hardware is space grade. Simplified, this means that it's been manufactured to better deal with radiation. But the concept is still a basic computer. This means we can build our own physical satellite simulator. While satellites come in all shapes and sizes, a common form factor is the CubeSat. It's basically a rectangle shaped satellite, and the default size is a cube of 10 centimeters on each side. This sounds small, but you can pack quite a lot in this. And if you plan on launching one of these, then it brings down the costs a lot, as this form factor is usually launched on a ride-share rocket. Think of it as the Uber of satellites. You hitch a ride with lots of other satellites on the same rocket, sharing the costs. The internals of a CubeSat is divided into many different boards, each with its own function. A lot of these boards are very similar to other satellites, because they all need the same basic functionality, including power management, a transmitter, and then it will differ with different sensors based on the function of the satellite, and even a camera. You can easily build your own. Think of it as a simple Raspberry Pi connected up with some sensors. If you want to go a bit more extreme, you can even look at the CubeSat Sim project that's been developed by Alan Johnson in the UK. He has designed a DIY satellite by making use of a Raspberry Pi and various off-the-shelf modules. Add a few solar panels and a nice 3D printed frame, and you have a replica of what is typical a CubeSat, except that it fully works in the same way. The project also consists of different boards for different functions, including a main board with the Raspberry Pi, which doubles as the main controller but also as the transmitter. Other boards include power management for the solar panels and charging the batteries, and then lastly the payload that you want on the satellite. This can be as simple as a few sensors to measure environmental factors, or a camera that takes photo of the Earth. This is a very simple DIY project that gives you a satellite right on the bench that you can program and experiment with. Ideas for development projects can be, for example, using the camera to orientate the satellite to the stars or sun, or to make sure the antenna is always pointing to the Earth. Or maybe you would like to design a payload that will monitor signals received from Earth. Or how about a relay that transmits messages received, a satellite messaging system? You are literally only limited by your imagination. As you can see, there's lots of different projects that can be done from everything I've mentioned up to now. Doing projects like this enables you to learn more about developing software for space applications and also build up that experience. Now, based on all of the above, I do need to talk about the legalities around all these experiments. The reality is that commercial companies with their own satellites won't like it if you start messing with their satellites. Tracking and receiving data is usually not that much of a deal. Important satellites will have security and encrypted data, but be smart about it. If you want to stay completely legal, then consider getting your amateur radio license. This means that you can legally receive data from all satellites in the amateur radio frequencies. It also gives you the capability of actually transmitting data to or via these satellites. Getting an amateur radio license is pretty simple and cheap. You basically need to write a test and do a small practical with radios. The written test happens twice a year, with the next one being on the 21st of October. Reach out to the South African Radio League to find a club in your area that can help with the practicals around the radio amateur examination. And above all, feel free to reach out to me if you need any more information on getting your license. With the ability of being able to legally transmit to satellites, you can do so much more. For example, myself and a few other enthusiasts use a geosynchronous satellite to have weekly chats about various technical topics. But it's not just talking over the microphone. This satellite has digital video capabilities, so we basically video call each other using the satellite. No internet required. This specific satellite has allowed me to do other fun projects such as receiving and decoding video and other media. One of the fun projects with the TV side of the satellite was to build a receiver. It works pretty much the same as a DSTV decoder, but it was a DIY kit that I could assemble. I've also developed various applications for the specific hardware. This is another topic in satellite development that I learned quite a bit from. Okay, so here's an example of what it looks like receiving it. So the software that's running is called OpenTuner. It's some software that I developed that communicates with the different hardware that we use to receive from the satellites. And this specific satellite currently I'm receiving 2 video feeds. You'll see at the bottom it's a launch video. So that's the original SpaceX launch video from back in 2019 when they launched this actual satellite. So it's playing on a loop because of it's a beacon that you can use to tune in your hardware. On the top is Phil M0PIT, and he's busy chatting there with somebody, and that's a live feed. it's the exact same concept as how you would receive DSTV, except none of it's encrypted, of course. It's all open. But this is the type of video calling example that we use the satellite for. So we can chat with people all over the world and share experiences and videos and media and stuff like that. So it's a lot of fun. The specific satellite I'm referring to is the QO100 satellite, which is a geosynchronous satellite launched by a company in Dubai. They have graciously allowed the amateur radio enthusiasts like myself to add a payload to that satellite, which we can now play and experiment with. You can chat with other people, transmit and receive data, and do so much more. It's currently one of my favorite satellites to play with. And being a geosynchronous satellite also means that it's always in view, unlike our other LEO satellites. Another fun satellite to play with is the Green Cube satellite. This satellite was designed to experiment with growing plants in space. Yes, there's actually something growing in the satellite. As a secondary mission, they also added the payloads which can be used to send messages to others while also listening at the same time. Basically, it retransmits a message that you transmit to the satellite. This satellite specifically is in a medium Earth orbit, so it's quite high, but it does mean that when it's in view, it will be in view for almost an hour when it comes over your house. Other fun satellites transmit images of the weather, photos taken of the Earth. The amateur radio frequencies are commonly used for enthusiasts, radio clubs and universities to launch satellites with all kinds of experiments. As mentioned before, the International Space Station is essentially also a satellite that you can track and communicate with. It has a voice repeater on it that you can use to chat to other amateur radio enthusiasts. Remember, transmitting requires a license. And if you're lucky, then you can chat to an astronaut. During July 2022, I was lucky enough to chat with Kjell Lindgren, an astronaut on the SpaceX Crew 4 mission, in which he spent a few months on the space station chatting with people all over the world. I even got a confirmation postcard from the Amateur Radio International Space Station team to confirm my chat with him. It was a very short conversation because I only had the space station in my view for about 10 minutes, but it was quite an adrenaline rush. I'll admit this presentation is fairly broad, especially if you consider the amount of different aspects of development that you can do with regards to satellites. Whether you're interested in tracking them, communicating with them, or design and develop on a satellite, it's all very possible to learn more about it from your home in preparation for one day getting that job in satellite development. And even if you are not interested in going that way for a career, it can still make for a very exciting hobby, and I can recommend that everyone go play with a satellite or two. These are exciting times, so make sure you don't miss any of it.